Good afternoon, everyone. Today we are going to have Professor Manoj Harbola from IIT Kanpur, who will be delivering a Bose Colloquium, a very creative kind of experiment come, a demonstration come, theory of very basic science and very basic physics. So I request our director, Professor Manoj Harbola, to kindly introduce the speaker.
I think these Bose Colloquium, we have last many years, many Bose Colloquium. But this Bose Colloquium is special on two counts. First is this is going to be given by a governing body member. And in fact, in our governing body minutes, it's minuted that the governing body chairman encourages the members to deliver Bose Colloquium. And certainly that message, one member has taken it very seriously, and we are going to have this Bose Colloquium from one of our governing body member. And it is special on a second count is that to best of my knowledge in Bose Center, there has been no hands-on talk. This will be a talk which we call hands-on because he will demonstrate something together with whatever he's showing with his slides or whatever he's saying. So I don't think we had, this is the first kind of this talk that will be given. And as already mentioned by Professor Mitra, he is a professor in IIT Kanpur in the Physics Department of IIT Kanpur. I know him for a long time, but I knew him as a specialist who will work with really the deep methodology of density function of wave, which was a very, very mathematical subject. And today, when Rajiv told me that there will be a talk, I said he is going to talk about density functional theory, which is very mathematical. I don't know how much appeal that will have to the general audience. But then I was very surprised to look at the title, which is. That's why probably there are so many people here. It's bubbles, soda, whiskey, and wine. If not for the first two items, for the second two items, there will be many takers. So we are really, really looking forward to it. Very exciting. And the stage is yours now, Manoj.
Okay, thanks a lot. Thank you very much. It's always a pleasure to visit SN Bose. And, thank you. And I take pride in being a teacher, so it's governing board member for us. Feel embarrassed. And actually, I believe in survive leadership and survive governance. So I'm at your service. Stop me wherever you can, wherever you want to, and I'll also keep calling you. Right now, that if you are here to, how do I do that now? I switch this off and go to my talk. Got this, okay. 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 So, now, if you're thinking I'll talk about bubbles, I'm going to talk about all these topics. Okay, so whoever wants to leave, please. These are the no, I'm just joking. These are the titles I took from various articles and all that. This is the current top-level physics. Talk about Fermi surface topology. Talk about superfluid helium, quantum engines, and what have you. But and we kind of work on that. But what I want to emphasize, in particular to the student body, there's tons of physics around, and those of us who work only in non-registic regime, there are 7, 8, less than 10 equations, and you should be able to reduce everything to that. But physics is very rich, right? So you have to connect between different things, and that's what you ought to do. So all this is, I mean, I'm going to use this phrase in a different way. There's plenty of room at the bottom. I mean, finance it in a different way, but we do bottom level physics also. Let's have fun at that. Okay, it's beautiful. You observe, you look around, and tons of it comes in all journals. And you can, and particularly again to student body, it is very easy to understand. They also check your basic understanding. But their applications are enormous, as I'll show. Okay, you can also help your engineer friends, you can help your technologists if you have these basic things on your fingertips. So do that. Once in a while, it helps to have fun. Then you go back to your 12th grade, you start enjoying. So let me start with the first question. Wonder about, why do T-Rex have such long tails? Why do you think Tyrannosaurus Rex, this have huge tails? There are no wrong answers. Any guesses? You see these pictures, you're seeing it all around. That's what I mean. There's some principle going on here, right? So you have to understand what's going on. And you go further down. What is the common scientific principle between the two? Have you seen this? Tightrope walker, right? There's a common principle. So let's now hear. I'll give you a hint.
For balance.
Participate. Otherwise, why soda treatment? I'll come and start sprinkling it on
I
you.
can hear some whispers. Speak loudly.
Speak loudly. There's nothing
For
wrong.
maintaining
Right?
balance.
Huh?
For maintaining balance.
And let's talk about CG, right? So T-Rex now you'll see it in a different way. It has long tails because it has only two legs, and it has to balance its heavy head with the tail, right? And this was used by people who made pyramids. That's an engineering application. They talk balance. Nobody knew about it, but they started doing it, right? So that's one. Let me just show you this. All right. So for that, I have the speaker, and I want to ask you. Somebody help me in this. Let's pour some soda in it. All right. Okay. And what I'm going to do now is, hope we didn't eat them. Where are the lasers? We're going to pour some raisins in them, right? Pour down them. So just leave it. And you observe what they do. Okay? That's why I said come forward. You see what they're doing? They move up, come down. Move up, come down, right? Why? What's happening? And why is it? Why not peanuts? Anybody? See that? It will keep on going on for half an hour if the gas didn't go out. Okay? Let's have a discourse. Let's have a discussion. I want smiles, yeah.
It's porous and it can the water by which the gas, when the water is absorbing it from soda, so it has zero weight, it rises, but due to weight it comes back.
Where does that soda go if it is absorbed? Does it suddenly do? Huh? I said I want smiles on the faces. So, yeah, anybody else? So what is happening is, one, is the bubbles. You see, soda, if it goes in, it's water, it will become heavier. It's the bubbles which are coming out, and raisins have these wrinkles, so they get stuck. And therefore, buoyancy takes it up. As it goes up, bubbles break, it comes down. Okay? So there's something, I'll just leave it here and see. So the other thing, right? Now, if you do that, there's the bubbles, right? That's my first thing. Now, you saw, seen all these bubbles around, they show colors and everything, but I'm interested in something else. I'll take you back to, and that's why I said you go back. There's this physics magazine which comes on APS site and gives you significant new stuff. So this is taken from there. Using a bubble blowing apparatus, researchers developed a model that explains the effect of several factors, such as breath velocity, you blow it, right? Process of blowing a bubble, right? And we'll see some of those, okay? So that's one. So we'll talk about bubbles. Again, you look around and see how they form. Bubbles do something more. You know, when I put them here, you hear the sound. There's a sound here, right? Bubbles make the sound. Why do they make the sound? What is the frequency of that sound? Can I use it in any way? Right? That will be the other thing. And you will see, actually, somebody used it to find out the quality of champagne, right? So here it is, champagne acoustics. What they did was, okay, let me go to the here is this champagne glass. You put a hydrophone in. Okay, can somebody tell me the cost of a hydrophone? It's not a, that's why I didn't ask for it. Minimum 35,000. Okay, I bought it for some project for students. You put it in and you measure the frequency. Right? You measure the frequency and you see the period of oscillation. The bubble breaks, it makes noise, and then the whole thing comes up. Right? So these bubbles are making noise. Can we use them? Somewhere we talk about that. And what this fellow did was he measured this is called Bose champagne, right? Measured how these bubbles are, for how long are they remaining. So we measured the frequency, which is about 7 kilohertz, and with time, how the number of events per second going down. And you see they remain for a long time, 4 minutes for quality champagne, right? So you can use them in a different way. And this is from Physics Today. Then recently, 2021, those of you who are interested, there's a beautiful physical review journal club, Sound of Effervescence, right? Where champagne gets its sound. Again, bubbles. The previous one is something called the ringing of bubble. It's the bubble vibration. The second one, this one, is crackling sound when it comes to the top. And that's something called the Helmholtz resonance. Okay, it makes a cavity that's giving you the sound. So you see a lot of physics going on. And these are all useful things. Particularly if you're dealing with paints, liquids, engineers use them. But this is absolutely basic physics. That's the message I want to give you. Next, the item everybody likes. Good about whiskey. Okay, forget this part. This part is not relevant. I just made it here. Okay, we'll talk about how we can use this usefully in some applications. Right, so that's the whiskey part. And finally, so this also came in Synopsis 2016. As a whiskey drop dries, okay, it makes the pattern which is very uniform. That's surprising. Why does it do that? Why do you think it's surprising? Okay, we'll talk about why it is surprising. So, they tried different whiskeys. A combination of molecules and liquid ensure especially uniform deposition, and finding that would inspire coating technologies. Imagine if this was not uniform. Imagine the paint you're putting on the wall if it was not uniform. If it was like notches. Imagine if you have an inkjet printer, the drop that fell was not uniform. It will be a problem. So, coating technologies, very important. And how do you do this is, I'm going to show through wine. Okay, so that's images from the internet. Wine shows something called the tears of wine. Any alcoholic drink shows that. Okay, and that's used to make this whole thing uniform. I'll talk about that. All right. So These are known as tears of wine, and I would like to. So what I like to do is, if you pass it around, if you promise not to drink it. Okay. So what I want you to do is turn it around a bit, and after that, this image should show. Whom do I trust? The director? Look around and see if this comes, and if you get the tears of wine, I'd like you to come and show it. Hello. Nobody's taking your picture and sending it to your parents. Okay, so do it. Here. Just roll it around to see if you get that kind of pattern. Okay, and I want you to show it, and after that, if you get it. Usko hilao thoda sa. So it goes up and then leave it. Then you'll see that the tears of wine are going up. You get it? छोड़ दो उसके बाद. You wipe them off, wash them down, and then off. Leave it for some time. So I'll let you experiment with this. Right. And all this stuff that I'm going to talk about, I've taken from top-class research journals. Okay, you talk about Physics Philosophical Magazine, Physics Today, Langmuir, Geophysical Research Letters. All right, I mean, this is across Journal of Chemical Physics. So there's the title after all this setup. Bubbles, soda, whiskey, and wine, and I've explained why I'm talking about these four. All right. So, plan of the talk is I'll talk about bubbles, their formation, how they are formed, and how that is verified. All right. In soda, I said ringing of bubbles. We'll hear that. Then I'll talk about whiskey. That will be on drying of whiskey droplets. Wine, tears of wine. If any one of you has seen it, please share it and show it around. And back to whiskey. Why that uniform deposition? Right? Now, I need volunteers to make bubbles. No, no. I have to go back and show it to people also. We got this bubble gum gun today. पीछे दिखाओ ना उनको देख नहीं रहा. Did anybody get tears of wine? पीछे. You're going like the frozen movie. पीछे. So I want you to notice something about these bubbles, almost the same size. All right? This is not being done for fun. I want you to observe. All right? Almost the same size, and something is blowing the air, and they're coming out. Film is breaking. Okay, and that's what we want to see how that comes about. Okay. So I take you back to 2003. And so your student who made this problem for JEE. We are killed for that. People say, but 80% of the students solve it. And this was the problem was the bubble having radius surface tension T. Radius R is formed on the ring of radius T less than R. That's what we're doing right now. And the air is blown with some speed V. Air stream hits the wall perpendicular. Calculate the radius. Right? This again. I was going to make this paper and I saw some children making it and I kind of made this problem. And how does this happen? A lot of things that are at work. And again, all this is for great stuff. There's surface tension, which is energy per unit area. Right? Energy per unit area required to create a surface. Liquid drops are spherical because that requires the least expenditure of surface energy. Or you can think of it as force per unit length on an imaginary line between two liquid surfaces. If the same liquid, then the force is equal on both sides. The liquid is different, it will get pushed on one side, and we'll see that. Okay? This is best observed by creating a real line. We'll do that on the surface of two liquids. So, if you really, once you understand this, then solving the problem becomes very easy. Right? The surface tension of air is pulling it back, air hitting is pushing it out. The moment they become equal, this becomes slightly greater, the bubble just comes off. All right, and you do the mathematical calculation, 4 pi bt sine theta and all that, right? Leads to the radius with respect to b. This was the JE 2003 problem, right? And come 2015, there's a physical review letters, and that says that there's a critical velocity by which you blow the air, and then the bubbles that form. If you're less than critical velocity, right, nothing happens. The film just does this. This critical velocity, this comes out. Critical velocity comes when this roughly hemispherical, then get bigger. How do we calculate the critical speed? We see, again, take this hemispherical, calculate the force, the sine theta, cosine theta, the works. This is quite easy. You can see a perpendicular force and its component and all that. And then you say when this becomes equal to L dash by the surface tension, you get the critical velocity. So that's all work grade stuff, JE stuff. Okay, all that balancing, and critical velocity comes out to be, remember this, 8t over the radius of the ray times the density of air squared. Right? That's what it is. Very simple 12 grade stuff. But why is it PRL? Right? This is a PRL. So this was done in this generating soap bubbles are blowing on soap films. Physical review letters 2016. By the way, I sent them after this JE problem. I said our students do this. And he was also very nice. He sent back saying, I'm very happy that your students are at this level. Right? So what did they do? It's a French group. They took soap solution right here, passed it through a frame so that there's a film made. And then they started blowing air through this nozzle, which has radius R0. Okay? And then they started doing the calculations. They wanted to check this. And then, obviously there's a pump which takes it back, and then it just keeps going. So this is, with that critical speed that they calculated, 80 by rho p square root, this is what happens. Let me run the film for you and you'll see what happens. So let's run this film. I hope I can do this. Okay. Where do I go with this? Highlighter, no, pen. Eraser. Where do I go with it? Does this go? I have. So let's run this. Start. So you see this as the speed, blowing speed less than critical speed. Nothing is happening. It just gets distorted. That's it, stops. Right? This ran for some time. That's it. It's run fully. So it's not moving for how long it's put on. I think 400 some seconds. Okay. Now what do I do? Go to the next slide. And then you measure the critical speed, whatever they could measure it, and then plot it against R0, the radius, and the slope is exactly -0.5. That's why it's a PRL. Okay, they could confirm this. And then for different gases, they calculated the critical speed and plotted against that 8t divided by rho R0. The slope is exactly 1. Right, so confirmed.
So
Right?
about the calibration, so it's the density of the
Density of the air. But that's what's giving the momentum transfer. And then, if you go above the critical velocity, you start making bubbles. Right? Please run this film. Please notice how they are being done. Now this is greater than critical speed, and you see exactly what we have, the figure we are making. This does exactly that. Right, so it's blowing it out, and then it breaks off. Blowing it out, it breaks off. That's what they measure. info is coming. Now, as I said, these bubbles make sound. And what I'd like you to do, I hope you have brought your mobiles, pour soda in these, all right, and record that sound. So I want to make a point to that later. How can I hear that? Here. Take. Record. I'd like you to play it later. Mobile also. So record it, please. This is not a ensign question or something that you're scared, right? तो खत्म हो जाओ. Here. Give it to a lot of people. Record it and keep it. You can show it to your friends later. Please record it, and I'd like you to play it later. And once you recorded it, I'd like to hear it. Then we'll play it again later. Did you record it? Play it on this. Here the point. Okay. Here's the point now. I like you to play it later. It should be like that kind of sound. Okay, so now that we're doing it, let me keep going down. So you hear the sound, right? Buzzing sound. I think I recorded it. I can play it. Where does it come out? Okay. So where does it come from? It comes from these bubbles vibrating, and this problem was solved in response to Lord Raleigh's calculation by Mr. Minard in 1933, and you will see at that 2015 it found application. So you do it out of curiosity, and then you suddenly find there's an application in some place we don't even imagine how it comes, right? So Lord Raleigh had said, some very high frequency. He did this calculation, he checked it through experiment. Okay? It's a very simple paper in Philosophical Magazine. So what one is doing is, you see this solid line is the boundary that's going back and forth. So it's doing A sine omega t. Omega is the frequency. You can calculate it very easily, and trick is very simple. What you do is you calculate it's adiabatic process very fast. So you calculate the pressure difference and you equate it to kinetic energy of the liquid. You see this bubble when it's going out is pushing all the liquid from 0 to infinity. Calculate that kinetic energy. Equate the two. Because in harmonic oscillator, that's what's supposed to happen. And boom, you get the frequency. All right. So here's the frequency. 1 over r is inversely proportional to the radius. Gamma is the adiabatic constant. P naught is the atmospheric pressure. Rho is the density of the liquid. And this gives a frequency of the range of 1 kilohertz to 7 kilohertz or 0.5 mm to 3 mm. It's very easy to calculate. Right? Again, 12th grade stuff. All right. Now, people used it. Now, you see, I said 1933 calculation, and look at this 2015. What people found, and this is from geophysical research network. Okay. What people found is, what this group found is that if the sound is loud, glaciers are melting. All right. And what they did, they took this ice from the glacier, took it to the lab, and measured the frequency. They let the bubble come out. So what they found is that this trapped air comes out, these bubbles do this vibration, and you get this frequency. All right? They did this experiment beautifully, and the relevance is environmental. The relevance is it's very nice how different things are connected. Sea lions do breeding near these glaciers. The reason is very simple. Sea lions are hunted by whales, and whales do it with their radar off, so that sea lions cannot catch them. When they do it behind these glaciers, there's so much noise, all right, that whales cannot hear. These sea lions make a lot of noise. And wherever the glaciers have melted, sea lion population has gone down because whales are hunting them. This is a very important study. All right. So this 1933 study comes back, 82 years later, and makes the significance. So I played this sound to you, right? I'll play it again, and you can. Has somebody recorded it? Yes. Please come and play it. Why should I play it? Who recorded it? Oh. Okay. Let's play that. Anybody else? Yeah. Play it out loud. That's it. ऐसे भी हो गया. That's what happens when you have too many options. What? That's from soda bubbles. And I want you to now close your eyes, or if you don't, listen to this sound. Sound of melting glaciers. How do I play this? Separate. So remember the sound that we played. I'll keep playing it. I did it very quietly, so mine is very good. You can see this is all soda bubbles, nothing else. Okay? Exactly the same. Okay. Okay. So in a soda bubble, and then a small glass, we created sound of melting glaciers. Tells you that exactly that trapped air which is coming out is making this sound. I don't really have to measure it. I can just perceive it, right? And that is environmentally very important because because this got a lot of traction. American Journal of Physics. How fast are glaciers melting? Just listen to them. Commentary in Scientific American by Stephanie Pappas on May 29, 2018 on this paper. The intensity, directionality, and statistics of underwater noise from melting glaciers, icebergs. The finding published in Geophysical Research Letters suggests that this commotion can be tapped for useful clues as to how quickly glaciers are receding as temperatures climb. Very important, right? Environmental warming. And thus, how fast global sea levels might rise. Now we can say it's not just great that we will listen to the noise, it's that we can transform it to a real tool in the future. Says the study leader, This is also done using satellites. This is so much easier. Just put some hydrophones around and see which direction sounds are coming from. This is very serious stuff. And in fact, if you type this on Google, it's very interesting. These people have started getting a lot of funding, global warming and what have you. So, people who have written, if you need funding in geophysical research, just write about bubbles, just write about bubble sound, so it's like that. So people are also not happy about it, but it became a very important study. Right, so that's bubbles for you. Now we come to whiskey. This is again from PRL. Controlled uniform coating for the interplay of Marangoni flows and surface acts of macromolecules. She got those tears of wine, but she never showed it. Saw that, right? Coming down? Yeah, so they're for real. Okay? This is called Marangoni effect. So a dried mark of whiskey droplet, gives the name, Macallan, UK, on a normal glass and a dried deposit pattern of Glenlivet, UK, again, Scotland, the fluorescent pedestrian particles. You can see this is roughly uniform. What is so special? I asked that question. Normally, one would tend to think that as the liquid metal drop evaporates, the residues would form a uniform stain. But it doesn't happen. What happens is, there's a coffee drop or a soup drop dries, it's a ring that comes around. Right? I mean, most of us when we eat dal, it drops on your shirt, or for girls, it's kurta, and you see it's a ring. Right? Why does that happen? And that ring is very harmful in a lot of matters. People also use it positively. But people who make, this blood slides, must have gone for tests. When blood dries, it also forms a ring. You don't get a nice, picture of whatever test you take. So this ring is harmful, known as coffee ring effect. All right, and this has to be stopped. Similarly, as I said earlier, if you have an inkjet printer and you get these drops with these lines around, there'll be a problem. So, for example, I did this experiment at home. Right, on a plate, I put this coffee liquid. This was around holy, so I put this holy color, and you see as it dries, you see that ring. Right, all the deposits have gone to the edges. All right, known as coffee ring effect. Let me show you this video. What is happening? This is really a nice video of showing the coffee ring effect. Show you what is happening. They're made in University of Pennsylvania. Yeah. Drops. Yeah. You see it's drying and you see the material going out. Important thing is these have to be spherical particles. As the fluid flows from middle to the edges. Now you really see a real microscopic picture. See how fast they're flowing to the edges. change the shape, it changes. You have ellipsoidal particles and so on, then you see something else happens. It's not coherent light, it's a little thicker, and you'll see what happens when you look at it close. This is real rock picture. Normal particles, what they're doing, making this way. They're going uniformly all around, and then eventually go back. There's one more reason for it, so let's. Okay. So let's try to understand this. A little bit of physics here, Fick's law of particle diffusion, thermal diffusion, electrostatics. And you'll see, I want to make a connection. I want you to see the connection that, as I said, there are only, 5-7 equations. You should be able to connect all the phenomena to that. So, Fick's law of diffusion says that the current is proportional to the gradient of the density, right? There's a diffusion coefficient. Negative sign because it's from higher to lower density. You put the continuity equation, and in a steady state when density is not changing, you get Laplace's equation for the density. Laplace's equation does not apply only here. It applies in other places too. For example, heat diffusion. Heat current is proportional to the gradient of the temperature. Right? Change in the temperature comes from heat flowing out. And in steady state, temperature follows Laplace's equation. And this is for students. I gave this I talk about this in my class in the introduction to electromagnetic theory. To always prove this uniqueness of the solution of Laplace's equation, given boundary condition is the same. So, question I ask is: suppose in this room I make the top 30 degrees, this side 40 degrees. Different times when you walk in, would you find different temperatures at different points? The answer is no. That tells you the answer is unique. Right? So that's the uniqueness of solution of Laplace's equation for given boundary conditions. And similarly, electrostatics, I know that is square phi is 0. Electric field, which is like the heat current or the particle diffusion current, is gradient of that phi. So phi, electrostatic potential, is the same as the temperature, is the same as the particle density. Current, heat current, and electric field are the same. Equation is the same. I am just replacing the quantities. Their answers, their behavior should be exactly the same. That's what you see. Solution to Laplace equation near an edge. This one always knows, I'm 10, 12, you just convert this in. The lightning conductor has these sharp edges, but electric field is maximum out there. It attracts all the charges. Lightning just goes through, right? Same thing should happen in diffusion of particles near edges because the solution is the same. Heat should be the same. Let us see if that happens. I'm going to show you this. Okay, so what we made is a wedge of paper, put potassium permanganate on this all over uniformly. But you see where the diffusion is taking place from. We'll see it slowly. It takes place from the edge. Right? That shows you that current is maximum near the edges. Nothing, it's the same mathematics, Laplace's equation. To make this, I want to show you something interesting. If you want to have it like a movie, I'll show you. Go back. I also have a song running on it because I was recording it. Okay, so anyway, so next one is we made the wedge sharper. Sharper you make it, more the diffusion current. And we'll see that. Now you see the edge is sharper. And you compare with the previous slide, now you can see diffusion is much more. Okay, sharper edges give you more current, diffusion current. It's not a steady state, nothing like that, but it gives you a picture what happens, right? So you can see it's much more intense current. So I just showed you the solution of Laplace's equation near an edge. Okay? Okay. And you go further down, related phenomena. All of us like this French fries, lunch maybe are. And you see all the edges are dark. This is from American Journal of Physics. These are homemade. So, okay. So you have to do the experiments at home. So you can see that edges are dark. Again, we are solving Laplace's equation. What happens is when these potato wedges go into oil, water diffuses. Water is coming out. And where would the current be highest? At the edges. So edges become dark. Right? So I've shown you solution of Laplace's equation in two different situations, but the result is the same. Right? Then another lovely thing. Look at the ice cream melting. See diffusion. Again, you pour it, and where is it melting from? Edges. Because the heat diffusion is maximum from the edges. Heat current is maximum from the edges. Right? So, same equation, del square something equal to 0. At the edges, the gradient of that quantity is the maximum. And electrostatic, this is what we are, 10 say, this is precisely what happens in a water drop. Water drop, the water is diffusing, it's evaporating. But we have these sharp edges out here. If there are these sharp edges, and if suppose this whole thing is pinned, that's where the maximum evaporation is going to take place from. If maximum evaporation takes place from there, water is going to come out like this and take all the colloidal particles up to that edge, and that's Cochran effect. Okay, this was a Nature article, and you can see the importance. Why it was so? Because it's very important, technologically very important. So you see this water going out and making this Cochran. Now I want you to see the title of this paper: Inkjet printed line morphologies and temperature control of Cochran effect. This is just to create that effect, that how important this phenomena is technologically, right? So with temperature, you can see the uniformity coming and all that and so forth. Okay. How can we control it? That's where this wine business comes in. Marangoni effect reverses Cochran positions. This is from Langmuir and all that. This group of Huahu is really at Michigan. That's been working on this quite a lot. But after I was discussing with a colleague who had done, he said, "Oh, I've done PhD." Nice. So, are you guys convinced that these tears do come? Did you see that? You did? We never showed it. You should have shown it. Huh? Anyways, so these tears come, and I'll explain why that happens. This is surface tension. So this is known as Marangoni effect or tears of wine, and this was explained in a thesis. All right, at Padua University long ago. Okay, by Mr. Marangoni. Marangoni observed it, somebody else showed it. So surface tension gradient. So in this, you have created a surface tension gradient, and I'll explain why so happens. That causes liquid to flow from surface to lower surface tension to higher surface tension. We show that. And again, the surface tension line, force, and everything. Larger area of lower surface tension means lower energy. So that's what happens. So let's show this. So let's put some water in here. Okay, this is water. And what I want to show you is that the liquid with lower surface tension spreads. अच्छा हाँ कैमरा में लगा दिया. आइए भाई कौन आएगा? Who's going to come? Somebody? You going to do it? So do that. Let's put some. So here's the soap water, right? Which has lower surface tension, and we have this little port out here, and he's going to put liquid in the center and see what happens. Just runs away. दूसरा लगा. like this, if it can go straight, then everybody will be able to see it. Yours stress, not mine. Because the water has now gotten this soap, so it's less. How do we throw this water out? You're better experienced than I. They're going out. Okay. Put a little more water here, more water, and then he'll show you the boat. So let's put it here. Okay. Right. Yeah. This. You see, this just runs away. That's because liquid from lower surface tension is spreading out, and it pushes the boat the other way. Right? Okay. We'll show them another thing. Right? This is process going to this speculation come here. Yeah. What we are going to do is pour water on this. Again, show you that lower surface tension water liquid goes out, and we are going to spread some black pepper on this, and to be honest, just put it in the center. You can just put your finger and put it there. Focus from our. You see the gap opening up in between, right? So the liquid with lower surface tension just pushes other things out, and this is what people are going to use to reverse that coffee effect. Okay, again, very serious business. Okay, idea मिल गया ना? Not the idea. Okay. So, let's go back. How do we use this? It's very ingenious. Go down. Now let's come to this. Okay, now what happens here when I asked you to swirl it around? Now this is a mixture of water and ethanol. Ethanol has lower evaporation, it evaporates much faster. So as the surface, the ethanol evaporates, what is left is water that has higher surface tension, right? Liquid is going to flow from lower surface tension to higher surface tension. So liquid starts flowing up, and then it cannot sustain itself, it comes down. Those are the drops, tears. Okay, so if I can create a surface tension gradient, I'll win the coffee effect. I have to make sure that on the edges, surface tension is less, it's more on the side, so then the thing starts flowing back, and that's precisely what people did. You know, temperature, and if you mix surfactants, you know, the surface tension changes. So here it is. Look at this drop, right? And you have mixed certain surfactants in this. All those surfactants are coming to the side when the water flows. As they come here to the edges, the surface tension out here becomes less. Liquid starts going up. You set up this current. Whole thing is reversing, right? So this is one way, and this is actually majority of papers say this. To create a surface tension gradient, you do this Marangoni effect, and you get this. All right. Now, this is the profile. Upper one is the profile of this liquid flow. This is a real picture. Lower one is a simulation. Okay, and you can see it's very much similar. So by controlling surface tension at different points, you can actually undo the coffee effect. That's technologically important. Sometimes when you contaminate water, it's suspected to reduce the Marangoni effect significantly. Then you see, you get the rate. Okay. So now recently, I saw one paper. This was presented in American Chemical Society, and they said if you want to check the quality of different tap waters, just dry it on a plate. Right? If it has a lot of contaminants, it will be uniform. If it doesn't, it will form a ring. Right? So you can make out very easily whether water is good or not. Now, surfactant induced Marangoni. This is so a little bit of looking up. Again, they're showing how the surfactants are making the whole thing drive like this. All right. So you see, initially this whole thing comes here. I'll show you a movie where you see it more clearly, and then it starts detaching and going back. That's what we show, right? So achieving uniform deposition using binary mixture as a solvent. You will see that this is pure water-based ring. See a ring out here. You make something called DEG. Okay, I've forgotten the name now. It makes it more uniform. If you mix FA, another surfactant kind of thing, this whole thing becomes uniform. There's a lot of work going on in this. All right, and it's again very simple things what you observe around you. And this is a picture I don't want to explain. I'm going back to the whiskey droplets. Okay, what you see is when this droplet comes, there are all these vortices being set in. That's because of all these effects I talked about. The whole thing is not just going out. Right? There are different places. Obviously, it's a droplet which you don't control everything. So these vortices set in somewhere. There's some gradient of the surface tension and all that. Finally, however, when all the ethanol has evaporated, the whole thing just goes out, evaporating back. All right? That was the experiment. Let me show you a movie. This is ethanol-based movie. You see the things coming back. Okay, a lot going on. There's a real stuff. There's a real drop. Okay. And once the ethanol goes out, you'll see the whole thing will just go to one side. You see the ring forming. See now, something is coming back in between, right? And it stops here. After all, after everything goes away, this whole thing becomes a ring again. Does ethanol also reverse? This is a small drop. Let's look at the large drop. See how much activity is going on inside. So you look at a drop and so much is going on. All right? And here also ethanol is actually reversing the coupling effect. You see nothing is getting deposited on the side. That's because of this Marangoni effect. Then finally something happens. Okay? But it's certainly not pure coffee. And here is surfactant in whiskey reversing coffee effect by creating surfactant-driven Marangoni effect. See. Now. Initially, everything is coming to the side. As more and more surfactants move here, starts detaching, starts coming back because now the surface tension out here is lower and it's larger in there, so it's coming back. All right. So you can see how much technologically important this is. And this is another, same kind of stuff. I'm not showing you this movie. See one more. Surfactant and all that. It's nice to see how motion is taking place inside, but this becomes roughly uniform. You see. One more, and that I think that this is surfactant plus ethanol. See how the thing starts coming back. All right. So this becomes roughly uniform. Deposition pattern of whiskey, DI water. They took a model water in that whiskey paper. They took whiskey, and this is the deposition in density with radius from the distance 0. All right. So you see, DI water is like this. This is model liquid. This is whiskey. They are roughly uniform. So that, the study is done and shown that if you have macromolecules, if you have these things sitting around, so I thought, why not do myself this thing? Same liquid that I had earlier, I put a little bit of sugar solution in, so that there are polymers inside and it's a surfactant. You see the drop becomes uniform. In dilute solution, same thing. So that affects. Okay? And so finally I'll conclude. G.H. Hardy in this book, Mathematician's Apology, very thin book, read it whenever you get time, says that how do you determine a theory is beautiful? He talks in terms of mathematics, but I'll just generalize it. That's why mathematics is lighter shade. We may say that an idea is significant if it can be connected in a natural and illuminating way with a large complex of other ideas. That's a serious theorem, he says, work which connects significant ideas is likely to lead to important advances in sciences. Right? What we have done here is the examples of bubble making sound, coherring laryngoly. We have seen how observations of phenomena across different fields can be understood by connecting them through the proper understanding. Here it was all Laplace's equation. Right? And take home message: observe, understand, connect, have fun. Need not do all the time those calculations. Right? Look around, and I thank you very much for your attention.
Thank you, Professor Harbola, for this exclusive talk. We learned a lot. Simple things actually teaches many things in the underlying laws of physics, how they work. So, we would like to take some questions.
Any number.
Any number. So, questions?
It should be coming. That's the only question.
Right?
Yeah, a spirited question. Diamonds are forever. The one movie, there was a very famous dialogue: martini with ice, shaken but not stirred. I would like to have your comments on the bubble point.
I like Martini that way too. That's the comment. Yeah.
So actually, there is circulation of
The liquid.
liquid
And the particles in it.
particles in it. So, but Laplacian equation generally doesn't give the flow
It's a steady state equation,
steady state.
right? So what I showed that if you have Laplace's equation in steady state, whatever that quantity is, phi, t, whatever, this gradient gives you the current.
Correct.
So from that we are understanding it. If I have to solve it exactly, we'll deviate a bit, but the general idea is there.
Okay.
The current would be there.
Current will be there.
It's just like the electric field is there.
But these vortices, the vortices,
Vortices will require it.
little.
More questions? First of all, I have this one thing. When you are forming the bubbles, so the simple thing is that the pressure difference between the inner and outer surfaces, which is given by this 2 gamma by r.
Right.
So can you not solve this one with that one only? The pressure difference between the.
Okay, when you're blowing,
Then there
when
is-
you're blowing,
there is it.
right? And so what you're calculating is open end, how much force is pulling it. That's precisely what one is doing. So, I mean, I do serious physics also.
Yeah. Questions?
Student should ask
Yeah.
questions.
I know one question he wants to ask.
Yes. So
Who takes that bottle? That's what he's asking.
And also, did these people check with the surfactant? So they are charged or
No,
it's
no,
nothing to
exactly.
do with this?
Yeah, Yeah. I said, I did it with sugar solution, Bose solution. I put good also. That also works.
Major thing is the surface tension.
Surface tension, yeah. And also sometimes the larger molecules, also,
Molecules.
the shape changes.
Because sugar, it doesn't have the surface active properties that it doesn't go to the surface itself. So maybe that sugar has the effect of macromolecule, but not
Yeah,
the surface.
yeah.
Yes.
So idea was that only.
That's
Because whiskey has these two things. It has those large polymers.
Yes. Yeah, there is a question.
You talked about this bubble formation, the temperature effect. So what is the temperature?
Say that again. No, bubble,
Temperature.
temperature in bubble formation.
Yeah, what will be the effect?
No, I never said this.
Oh,
The only thing that will happen is surface tension will change. So for the same blow, you'll get a bigger bubble.
No, but this equation contains a T, capital T.
That T was not temperature, it was surface tension. The others wrote as gamma.
Okay.
Some things stuck from calculator. That's always there.
In case of coffee,
In case of yes.
what are the controlling factors?
So there are two assumptions. One, that this thing where it's getting stuck, that remains pinned.
No, why they are stacking there? It is concentration or?
No, that's again the adhesive force.
So substrate playing a role. Some sort of.
So I don't think there is no more
Okay.
questions. So we thank Professor Harbola for this wonderful talk.